Hey there, how's it going? So in the previous video, we started to actually calculate some values for the gradients at certain points on the graph of y equals x squared. And some of the calculations we did will be kind of, like I said, foreshadowing the way that we're going to be proceeding. But we're just going to take a little bit of a pause before the algebra starts to ramp up a bit and take a bit more of a qualitative look at gradients of tangents with respect to the pattern that we started to see occur. So I'm going to sketch up. We looked at the graph of y equals x squared, and we calculated a few gradients at some specific points, and notice that they started to form a pattern themselves. So we had at the point where x equals 1, we had that the gradient there was 2. And then what we also calculated was the gradient when x equaled 2. At that point on the function, we found that the gradient was 4. Now, without doing any more calculations, we can find a couple more gradients on this curve. So using the fact that the parabola is an even function and it's symmetrical over the y-axis, these gradients here are positive because they're going up from left to right, but if we look at equivalent distances off to the left in the negatives, the gradients are going to have the same steepness, but just they're coming down, so they're going to be negative, right? So over here at -1 is going to have a gradient of the same magnitude or size, so it's going to as 1. So the gradient here is going to be -2, right? So same size, but just in the opposite direction. And likewise, if we go over here to -2, whoops, it's kind of, it doesn't quite line up, but hopefully you get the point. We've got that the gradient there is -4. Now, also, what's the gradient going to be here when x equals 0? Well, if we draw the gradient, the tangent line in, then the gradient there is simply going to be 0, right? Because it's a horizontal line. All right, so this is called, has a few names. It's in the context of the parabola, it's a concave up parabola. It's a minimum, but more generally, it's a turning point, or also we'll refer to it as a stationary point, because if we're traveling along the parabola, we're kind of decreasing and coming down, right? Negative gradients, we're coming down, decreasing. We stop and have a bit of a rest here, and then we go back and start increasing there. All right, so what we can do is do a graph of not the function itself, but of the gradient function, so a function which tells us the value of the gradients at specific points. So let's plot those points that we have so far. We have when x equals 1, we have that the gradient is 2. So we have a point there. Then we have when x equals 2, we have that the gradient is 4. Something like this. We have when x equals 0, the gradient is 0. We have when x equals -1, the gradient is -2. And we have when x was -2, the gradient was -4. So you can see that the gradients of the tangents at certain x values form a pattern and an equation, and it's in fact a classic, miss the points like I do in class, just draw the points a bit bigger so they hit there. And so this purple line is a function which is telling us the gradients of the tangents at these x coordinates for the graph y equals x squared. And so you notice that the equation of this line is y equals 2x. Like we did in the previous video, the gradient at x equals 1 was double 1, 2. The gradient at x equals 2 was double 2, was 4. And like I said, you could do it yourself, mimic the process that is. The gradient when x equals 3 on the y equals x squared parabola is gradient of 6 of the tangent there, right? Okay, so this here is called the gradient function of this other function. So we have a function, we can find gradients of the tangents at specific points, and they themselves form a pattern which we can identify a function for that as well. Okay, so we're able to do that because we had started to calculate, we done the legwork and calculated some values. So how could we kind of maybe identify, maybe not fully the exact equation of a gradient function, but at least kind of get a feel for the type of equation without doing any calculation. All right, so I'm just going to draw up another parabola again. This time I might just have it moved up. Let's say we've got y equals x squared plus 1. All right, so here's the type of analysis that we could do to get a feel for what the gradient function might be. First of all, we should notice the stationary points. Okay, so where is the curve turning around? And whenever there's a stationary point, we're going to have a gradient of 0. Okay, so here we're going to have gradient of 0. So this gradient of 0 is going to kind of break up the domain across the x input values into kind of two regions, to the left of it and to the right of it. So then we should see what's happening to the right. Well, to the right of this gradient of 0, we're going to have positive gradients, and you can see that the gradients rather, are getting steeper, so that means the number assigned to those gradients is going to increase and go up. Right? So we've got positive values to the right, and the numbers are getting bigger. Okay, over to the left here though, the gradients here are negative because they're coming down, and as we move left to right, the numbers are getting, so the size of the numbers, irrespective of the sign, the negative, are getting smaller. Okay, so what we can do, based on identifying the stationary point, and then from the regions broken up by the stationary point, what's positive and negative, we can approximately draw the gradient function, right? So the curve y equals x squared plus 1 at the x value of 0 has a gradient of 0. So we should plot wherever the turning points or stationary points are, the gradient function, that's where the x-intercepts are going to be on the gradient function, right? Now, to the right of here, we're going to have some positive values, and then to the left of here, we're going to have some negative values. Now, for reasons which maybe aren't perfectly clear yet, it will in fact be a linear function again. Okay, there's plenty of functions which could satisfy having an x-intercept here in positive and negative values, like maybe like a cubic curve. Okay, but just like over here, it's going to be a linear curve. You might notice that this was a squared equation, so a polynomial degree 2, and the gradient function ended up being a linear function, which is a polynomial degree 1. So the degree of the polynomial has reduced by 1. Maybe that happened by chance, who knows. Okay. So here we're going to have something like this. We're going to have a graph which has an x-intercept here. We're going to have positive values to the right, negative values to the left. And what's happening to those positive values of the gradients? Well, they are increasing, and the numbers are positive, but the numbers are getting bigger positive. And as we move left to right, the negative numbers, the size of them is quite big, and then they're getting smaller and smaller as they come towards 0, and then they cross over. Okay, so this would be some linear function, and in fact, of interest, it's actually the exact same, because notice if we translate this parabola up 1 unit, well, does the steepness at that x value change, right? Does the steepness of the curve at x equals 1, the gradient there, change from 2? Well, if I move it up, then the steepness seems to stay the same at those particular x coordinates. Now, maybe if I moved it across, then at a certain x coordinate, the gradient would change, but that's actually going to be the same, right? So notice x squared and the x squared plus 1 graph, they just differ by a constant, plus 0, plus 1. Maybe you should lock that away for later. All right, so let's maybe look at a totally fresh function and try and find its gradient function. All right, so let me draw in some random cubic curve. Okay, and I'm just going to say that this is the graph of y equals f of x, y equals some function. All right, so we're going to perform the similar analysis that we did over here. First, the starting point is going to be to find the where the stationary points are. Okay, so stationary points here are going to have a gradient of 0. And I might do these on the same graph this time. So these, right at this x value here, in line with where the stationary point is, the gradient function is going to be the value of the gradient at that whatever x value that is going to be 0. Likewise over here, the gradient at that x value is also going to be 0. Okay, and again, this now breaks the x-axis up into 3 regions, right, in between the 2 points to the left of the leftmost and to the right of the rightmost. So let's look at what's happening to the gradients. Well, to the left of here, the gradients going up here are positive. In between these 2 points here, the gradient of tangents along here are going to be negative. And then to the right of here, the gradient of the tangents here are going to be positive again. So what type of function might fit the bill of having 2 x-intercepts, starting positive, coming negative, going positive again? I mean, the way I just kind of visually drew it through is almost like a straight line, maybe an absolute value, but we'll find, just like a polynomial has a gradient function, which is also a polynomial, this is a cubic, it's also going to have a gradient function, which is a polynomial, and the pattern is actually going to be that the degree is 1 less, right? So we have a cubic is x to the 3, and so the gradient function is in fact going to be an x squared, a parabola graph, right? So we'd have positive values up here, hit the x-axis, have some negative values, turn around somewhere, and then come back and have some positive values. All right, so this purple curve is the gradient function, and just to introduce some notation, if this was our original function, y equals f of some variable x, then the way we denote the gradient function is f with a little dash, f dash x, read like f prime x, but looks like a dash, so it seems fine to call it f dash x as well. All right, so let's just double check that this makes sense as well with the size of the values as well. So here we've got positive gradients, but the positiveness of them, they're positive numbers, but it's quite steep, and then it's coming up and getting shallower. So the value of those gradients are going to be big numbers, positive, still positive numbers, but then become smaller positive numbers. Let's see if that matches on the gradient function. We've got some bigger positive numbers, and we get smaller positive numbers as we get close to this stationary point, right? Likewise over here, this side, we've got on the curve, we've got positive numbers, and what's happening to the steepness? Well, they're shallow, steeper, steeper, steeper. So to the right of here, the gradient function has positive values, but those positive values are getting bigger and going up. In between, we have negative values. So we have the gradient function is below the x-axis, negative output values on the y-axis. And let's again think of the steepness. Shallow, 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 getting steeper. So the size of the values are getting bigger. Over from this side, we've got, like, say, maybe going right to left on the blue curve, the original curve of the function. We've got shallow, 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 getting steeper. So on the gradient function, the purple curve, we've got shallow is going to be low values, becoming the size of the values is going to get bigger. And then there's a different color. There's a certain point at which the curve kind of turns around. So we've got shallow values, they're getting steeper, but there's kind of like a point at which they're coming down, and then it starts to turn around, getting ready to go back up. And so that's aligns with what that is, and that's called the inflection point where it turns around. Okay, that one's not too important rather, kind of at this point of your understanding, but it's just good to be aware of the kind of the main shape of the gradient function of a function, and just noticing that for polynomials at least, the gradient function is 1 degree less than the degree of the original function. Okay, so that was a bit more of a qualitative approach, sketching these gradient functions, and so in the next video we're going to actually go ahead and get started with doing figuring out the precise actual equation of a gradient function given a particular function. But that's it for this one. Then catch you later.